see my screen? Y'all can see my screen, right?
Yeah, we can.
Yes.
Okay. All right, so the second problem is called Bella's homework. So Bella has n homework assignments due at midnight, but unfortunately she has procrastinated and now only has T minutes left. Her Schoology homework assignments are numbered from 1 to n. Bella needs 8 assignments to finish the ith assignment. Due to the way Schoology is set up, Bella can only choose any assignment I to start working on initially, but then the next assignment she works on has to be assignment I+1 and then I+2 and so on. So in other words, all of Bella's assignments must form a contiguous segment in the array A. So basically the problem boils down to just finding the longest contiguous segment in the array whose sum of elements is less than or equal to t. So the obvious naive solution that usually first comes to mind is we loop through all the starting points of the segment, or we loop through all the elements in the array and treat that as a starting point in the element. And then, so for example, we start on A1 and then we do a linear search for the ending point in for that contiguous segment. So I guess I'll cut up the naive solution first. So let me get rid of this. Okay, so I already have the input here. So if we want to, so when we start, so I'm gonna start coding the naive solution. So we're gonna define some variables here. So maxi is just the maximum answer we found so far. Sum is the current sum of the contiguous segment, and then P1 will just stand for pointer. Okay, so now we're looping over all the starting elements in the array, our starting points in the array. And then I'm just gonna reset my variables here. And then we're gonna keep, so P1 is the pointer for the end of the segment we're trying to make. So we're gonna keep expanding P1 until the sum of the segment is, we're gonna try to expand it as much as possible without letting the sum of the elements in the segment go over t. So we're going to check that P1 is first less than n, and we're going to check if the sum plus the current element we're considering adding on is less than or equal to t. And then if it is, we'll add it to the sum, and then increment our endpoint. And then we'll say, we'll update the maximum answer we found so far. And then the length of the segment we found is just the end pointer minus the start pointer. And something to know is that P1 doesn't exactly point to the end of the segment. So if this is our current segment that we have, P1 will actually point to the one right after the end. So this would be like P1. Yeah, so then this is it for the naive solution, and we just have to print out our answer. And compiler. Oh, I'm missing a semicolon. All right, looks like I have bad test data because it still got everything correct, but it's not supposed to. All right, so the solution we just described is O of n squared. Since we're going to loop over all the elements in the array, and then for each element in the array, we have to loop over all the elements past it. So for each element there's an O of n loop, so that's O of n squared in total. And since n is supposed to be 10 to the 5th, an n squared solution would be like 10 to the 10th, which isn't supposed to run, but for some reason it did, probably because I made bad test data, which is my bad. So we want to get something less than O of n squared. So what we're going to do is we're going to use this technique called sliding window. And the technique is called sliding window because it looks like a window that you're sliding across the entire array. Okay, so to use the sliding window thing, we have to recognize that every time we try to find the maximum segment for for a given starting point. So say like, let's start at like A2, and we're trying to find where the endpoint is. The endpoint for like each of the starting points, they will always they will never be less than the previous one. So like this endpoint will never end up like here. Like this will never, the endpoint starting at A3 will never end up before the ending point for A2. So using this, we know that they always have to increase. So instead of for each starting point, we searching the entire array. We only have to search past the endpoint for the last one. So we basically keep track of P1, which will be like the endpoint we found last time, and then only search past there. So I will now code up the sliding window solution. So we can see in this solution that the asymptotic running time is only O of n because we only loop over each of these elements once. So that's O of n. And then the pointer P1 only progresses through each element once. So that's also O of n. So in total, it's also only O of n. So I guess I'll start coding that up. So it actually isn't that big of a change from the naive solution. So we're still going to use these three variables, maxi, sum, and P1. But now, instead of trying to loop through this whole thing every time, we're actually going to start searching from P1, which is what we found last time. So while the pointer is still less than n and the next element we add won't increase our sum over t, we add that to our sum, and then we increase our pointer. Then, if you want to keep your code clean and concise, you actually can shorten this all down to one line. And then we want to update our maximum that we found so far. And again, yeah, P1 minus I is the length of the segment. And then, so this will be it for the computation that we have to do for the current starting point we're at. But then we also have to make sure we update our sliding window when we do our next segment. So say we just finished doing the segment A2 to A4. Then when we slide our window, we're going to start at the new window at A3. All right, so then the sum is actually not going to include A2 anymore. So we need to delete that from the sum. So sum minus equals A1. And that should be it. Let's see if it works. Okay, it works. That's it. Does anyone have any questions? Okay, I guess if not, I'll let Daniel go ahead and present the third problem. Or